Alright, this is lesson 6.1 of AP Calculus AB, and in this lesson we'll take a look at two topics. You might be thinking, hey, didn't we do the fundamental theorem of calculus already? Yes, but there's a second part that I want to deal with today. And we'll also talk about these rate graphs, which are often on the AP exam, and how to interpret them and figure them out. So, we're going to take a look at the second fundamental theorem calculus first. And do you remember this notation here? ddx? Yeah, that's like a verb. Take the derivative of. Well, what are we taking the derivative of? It says take the derivative of the integral of the function 2x minus 3 dx. And I hope you remember that that's just equal to 2x minus 3. And if you don't, I would suggest you do the following. If I asked you to take the integral of 2x minus 3 dx, hopefully you remember from the previous unit, the integral or antiderivative of 2x is just x squared, and then the antiderivative of negative 3 is negative 3x. And of course we should have a plus c. This is an indefinite integral. Now, if I ask you to apply and take the derivative of this, you should be able to say, hey, you get 2x. And then you'll have minus 3. Ta-da! Same thing. Okay? So, let's look at the following examples, because it really serves as an informal guide to really discovering the second fundamental theorem of calculus. So if I ask you to take the integral from 0 to x of the function 2t minus 3 dt, then you'd be taking the antiderivative of 2t, which is just t squared. The antiderivative of minus 3 is negative 3t. And then you're going to now evaluate this whole expression from x to 0. So plugging in x where you see t, you get x squared minus 3x. And then plugging in 0, you're going to subtract, what, 0 minus 0. So ultimately, who cares about that 0? You just get x squared minus 3x. Okay? And now, if I ask you for part 2 to take the derivative of this integral, this part in blue that I circled, is really just my answer to number 1. So really I'm asking you now take the derivative of x squared minus 3x. You would then find that the answer is 2x minus 3. Ta-da! And my question is, do you notice anything yet? Noticing this and this. Taking the derivative of that gives you this. Still nothing yet? No worries. Let's try the next one. What is the integral from 10 to x of f prime t? So now I don't have a function for you, but I'm just saying look at f prime. What is the antiderivative of f prime? Well, hopefully that's just regular f, so f of t. And I want you to evaluate this from x to 10. And just like above, I would then plug in x wherever I see t, and then I subtract from that f of 10. Now once again, f of 10 is just some sort of number. Part 4 here says take the derivative of the integral of f prime of t dt going from 10 to x. That part I just circled in red is exactly what we had from example number 3. And so I'm going to ask you to take the derivative of f of x minus f of 10, and the derivative of f of x is just f prime of x, and the derivative of f of 10 is f prime of 10, right? Wrong. The derivative of f of 10. F of 10 is a number, so it's like a constant. The derivative of a constant, of course, is 0. So you're just left with f of x. Look, look, look. Started with f prime of t, taking the integral, and then taking the derivative of that, I get f prime of x. So can you see how taking the integral and then the derivative afterwards kind of gives you the exact same thing as what you started with, except now you replace the t with the x? Well, that's what the second fundamental theorem of calculus is really saying. For any constant a, okay, so that's the little a down there. If you're taking the derivative of the integral from little a to x of the function f of t dt, all you really need to do is replace the t with this upper limit x. And there you have it. And that's what we tried to show you above. Okay. So, can you now take a look at questions 5, 6, 7, and 8? Okay, same idea. So, we're going to do the same thing as above. The antiderivative of f prime of t is now f of t. I'm going to ask you to evaluate this from 0 to x squared, which means that you're going to plug in x squared for t and 0 for t. Cool. Number 6 says, hey, take the derivative of that. So let me just take the derivative ddx of, and I'll copy what my answer was in number 5. And this time now, if I ask you to take the derivative of f of x squared is f prime of x squared. And if you leave it like that, ooh, shame on you. What did we forget? This is a function within a function. Can you say hello chain rule with the extra hook on factor? Chain rule. And then, of course, the derivative of f of 0 is just 0. So ultimately here you get this. It's the derivative of x squared with an extra factor of 2x. Okay? Don't forget that. Okay, you do number 7 and number 8 because it's pretty much the same. Try it. I hope you're trying it, not just waiting for me. You should really pause this video and do it yourself first, and then come back and double check your answer. Chain rule. Chain rule once again. Oh, lots and lots of chain rule now. So with examples 5, 6, 7, 8, what did you notice that was different than questions 1, 2, 3, and 4? Hopefully you notice now that instead of having x and a as our limits to the integral, I've now changed them and had functions. So now instead of constants and x, now I got u and v, which are functions of x. Okay. And now notice that the extra thing you have now is, yes, you still plug in the function, but now you have these extra derivatives of the function that appear. Once again, reason, hello, chain rule. Okay. So remember those hook-on factors of chain rule? You got that here too. So really, the chain rule version is the one that also covers the version up top. So if you really want to memorize or understand one, just the chain rule. It covers all the different scenarios. Alright, so with this idea, you should be able to go and try to find each of the following derivatives of integrals without actually integrating. Okay, so don't go through that same process as I did. You should be able to apply the second fundamental theorem of calculus and boom, get the answer right away. Okay, so taking a look at 9, I'll do 9, 10, maybe 11 together, and then you can do the rest. The integral from x to 0 of 2t minus 3 dt. I would say, hey, look at the first part. It's always the constant on the bottom, so I can rearrange this as ddx of 0 to x, but if I do that, notice I actually have a negative now that comes out, so negative of 2t minus 3 dt. And then I can just apply the fundamental theorem of calculus. That's just negative 2x minus 3, and we're done. Or if you really like, negative 2x plus 3. Okay. 10's interesting because they're both numbers. So you're integrating a number and a number. The derivative of that, well, notice that this part will just be a number. So if I ask you to take the derivative of a number, the derivative of a number, of course, just equals to 0. So the derivative of a definite integral here is just equal to 0. Okay. I'll do 11 with you as well. So remember, the derivative of the integral from -1 to x cubed of the function t squared plus 2t dt. There, I would ask you to replace the t with the x cubed, so x cubed squared plus 2 times x cubed. And notice that x cubed is a function, so all of this has to be multiplied by the derivative of x cubed, which is 3x squared. And because you have a constant at the bottom, that of course just disappears. It's like minusing 0. And if you really want to simplify this a little bit, then x to the power of 6 plus 2x cubed, all multiplied by 3x squared. And that's good enough for me. Alright. I'm going to ask you to try 12, and then 13, and 14 on your own. Okay? And I would suggest you once again press pause, try it yourself first, and then come back and double check your answers with me. See you in a bit. Ooh, 14 is interesting. I don't use that ddx notation, but f prime just means the derivative anyways. So if the derivative of this integral, I'm going to plug in 3x squared wherever I see t. Lots of brackets here. And then don't forget, I need to multiply by the derivative of the function, 3x squared. And that should be it. I will simplify this to 1 minus 9x to the power of 4, all to the power of 10 times 6x. Got it? I hope so, because that's it. Alright, turn the page. Alright, our next topic for this section, the interpretation of what I call rate graphs. So graphs of rates, not functions, but rates are common in calculus. Most of the time the horizontal axis stands for quite a lot of things, but usually it's time. The vertical axis then of course stands for some type of rate, okay, often with respect to time. So, you know, something like in physics, here's my rate graph, the velocity, because it's a rate, right? With respect to time, who knows, maybe I have something like this. And then remember, a point on this graph then, so a point on this graph or this line will represent the indicated rate at a certain time. So this would be, for example, the velocity, or maybe 5 meters per second, right? Something per something. The slope of velocity, hopefully remember, is acceleration. So if I ask you to find the slope of this line, then that indicates the rate of change of the rate. So that's why, you know, if it's acceleration, it'd be meters per second, or meters per second squared. Now, the neat thing about this is the signed area. So the area between the graph and the horizontal axis. So that would be stuff like this here. This particular region is a definite integral, right? It's the stuff we've done before in the previous unit, which really undoes the rate. So the opposite of the rate, or the antiderivative of velocity, would be, yeah, distance, displacement. So the idea of that would be taking the definite integral of a rate produces an accumulated value. You're summing up a whole bunch of things. You're accumulating things. In this case, for velocity and time, you're accumulating distance. So the integral, and this is the key part I want you to think about, the integral is thought of as an accumulator, summing up a whole bunch of things. Okay? So to put this in better context, let's take a look at this one example here. And I'm going to now take a look, and this is an example of a rate, because notice here the y value is the rate of rainfall. How convenient for us here in Vancouver or Burnaby. And on the x-axis is the time in hours after midnight. So it says the graph right at the right models the rate of rainfall in inches per hour from midnight to 6 a.m. during a tropical rainstorm. Okay, so let's take a look at number 15. It says write a complete sentence to explain what point A on the graph represents. So here's point A. Okay, point A has an x value, or in this case a time value, that would be 3, and a y value, which stands for the rate of rainfall, which in this case is 1. So ultimately, you should say something like this: at 3 a.m., right? Because it's 3 hours after midnight. It is raining at a rate of, in this case, 1 inch per hour. And that's what that point A represents on the rate graph. Okay. How about 16? What's the slope of the graph between A and B? It's a flat line that's horizontal, so the slope is not 6, sorry, 0. And so what does that mean, though? Because number 17 says, tell me what it means for the answer of 16. Does it mean that it didn't rain at all? No, this is the rate. So the rate did not change. So I'll say between 3 a.m. and 4 a.m., there was no change in the rate of rainfall. Because once again, that's the y axis, a y variable. So there was no change in the rainfall. Just before at point A, it was raining at 1 inch per hour. So you could also have said the rate of rainfall, the rate of rainfall stayed constant and be more specific, I'll say at 1 inch per hour during that time interval. Okay. All right, try to see if you can do 18 and 19 on your own. Okay. The slope of the graph between B and C, the change in the y value divided by the change in the x, that'd be negative 1 over 1, which is just negative 1, and this would be the slope. But now let's interpret that. So how would we describe that negative 1? Well, I guess between the hours of 4 a.m. and 5 a.m., I'll say the rate of rainfall decreases, because it's negative, at a rate of, so remember, this is the slope of the rate of rainfall. So it decreases at a rate of, and it is 1, but now what is our units? It's not inches per hour, but inches per hour, or 1 inch per hour squared. So it's the rate, or the derivative of the rate of rainfall. Since our rate of rainfall was already inches per hour, another derivative on top of that would be inches per hour per hour. Okay, try number 20 and 21 now. Well, I guess I'll do that with you together, because this is something different. It's the integral from 3 to 5 of r of t dt. So notice this integral just represents that shaded region in our graph. Whee! And so remember, I say this as an accumulation. So this really is the accumulation of the area underneath that graph, but bounded below by the horizontal axes. And we can look at this geometrically, because I think from 3 to 4, I see that the width is 1 and the height is 1 of this rectangle. Really a square. 1 times 1. That's this part here, blue. And then how about this part in red? It's a triangle, so 1 base times height, which is also 1, divided by 2. So I think the answer is 1 plus 0.5, or 1.5. Now what's my units here? Inches. Good, because this is a total accumulation of rainfall. So I was getting ahead of myself. I didn't really need to write down inches here because I just wanted a number. But in 21 now, I'll say during the time between 3 a.m. and 5 a.m. it rained a total of 1.5 inches, right? An accumulation of it. Okay. All right. I'm going to let you try 22 and 23, and if you've completed those, double check your answer with mine, and hopefully you have understood these two topics really well. Go for it. 0 to 6, that's everything. But it says approximate, so I guess what I'll do is I'll just draw a nice line like this, because this is a nice shape. So a green triangle, how about 3 times 1 divided by 2, add to that the blue rectangle, 1 times 1, and then add to that the red triangle, 1 times 1 over 2. We get what? 3 halves, 1.5 plus 1 plus 0.5. That'll be 3. So I'll say something like during the time between midnight and 6 a.m. it rained a total of 3 inches. Yikes. I hope you got your boots. Alright, that's it.